everyone, my name is David Klee, founder of Sequilibrium. I founded Sequilibrium to create educational content from my personal experiences from over 2 decades of working in IT. I've been lucky enough to work in many areas of IT, as a systems administrator, DBA, consultant, and in a previous life, a not-so-good software developer. I often felt what was missing from the training space was a solution that was all-encompassing for everything at and under the database. There are some solid training offerings on a single layer of the system stack, but we all know that each layer interacts with each other and can make or break your system performance and wreck your licensing costs. As someone who has expertise in enterprise Microsoft SQL Server performance tuning with a serious focus on the infrastructure underneath the database, I knew there had to be a better way through a one-stop shop training to solve everyday frustrations, questions, and the siloed approach. So, I created the SQL Server on VMware Accelerator, a step-by-step course to do just that. Walk you through each layer to help you create the most predictable, resilient, and fastest performing environment. No other single course out there provides you the fastest way to get up to speed and learn about how each layer of the system stack works, while also creating the knowledge to be able to better collaborate with the other IT silos. So whether you're a DBA, system administrator, enterprise architect, this course is tailored for you, so let's get started. This is the introduction module to give us the right foundation for learning everything this course has to offer. The course agenda is lengthy but straightforward. We've got a solid 15 modules to go through in depth. I don't assume any prior knowledge of any of the pieces underneath the database, but I would like it if you've got at least a few years as a tech professional under your belt. I know the pieces underneath the database can be a mystery, so we're going to start with introducing enterprise virtualization and the system stack. As you get more familiar with the system stack, we're going to work from the bottom up to discuss the architecture and configuration, specifically for high-performance SQL servers, so that you understand the nuances of each layer. We'll be covering from the bottom to top enterprise storage, networking and interconnects, physical servers, the VMware ESXi host, the VMware host cluster, virtual machine configuration, both Windows and Linux operating systems, and then the SQL Server instance itself. Once our brains are thoroughly scrambled, then we'll talk through performance and availability tuning, the not-so-fun topic of SQL Server licensing, and then talk through how your operational practices can be improved through embracing everything we're talking about. My name is David Klee, and I am the founder of Sequilibrium. I'm fortunate enough to have been awarded both the Microsoft Data Platform MVP and the VMware vExpert Awards. You might ask why I'm qualified to lead this deep dive Accelerator series. I've been virtualizing SQL Server since November of 1999 with a copy of VMware Workstation, Windows NT 4.0, and SQL Server 6.5, and have had large production environments successfully running entirely in virtual platforms since 2004. I've been consulting around this convergence of infrastructure and data since 2010, and have worked on some of the largest and most demanding database servers on the planet. And after being in the trenches for decades, I'm here to make your life easier from my lessons learned, and not just with this course, but I've also got a number of methods to broadcast continuing education on this topic. Feel free to reach out if you have any questions or want to see additional topics covered in the future. We have to make sure everyone's lawyers and insurance companies are happy, so in the spirit of these folks, here we go! Please take the time to review this disclaimer now. Again, always test before making changes to production servers. All trademarks and copyrights of the individual products mentioned are owned by their respective companies. Also, it should go without saying, but the seed in this course you have purchased is for you and you alone, and the material is not to be redistributed in any way, as it has taken me over 20 years of study to prepare this training series for you. For this introductory module, we're going to be discussing just what is Microsoft SQL Server. We'll talk through my definition of virtualization, resources and queues, and then start talking about the specifics around the VMware vSphere platform. No discussion about SQL Server virtualization is complete without discussing both the benefits and the drawbacks of virtualizing enterprise databases. At this point, we'll describe in detail what comprises the enterprise infrastructure stack and discuss our performance and availability goals from a holistic standpoint of everything we're about to discuss in future modules. To get started, just what is Microsoft SQL Server? It's not just a relational database engine. There are many components inside the SQL Server suite, all of which have different use cases and very different performance characteristics. The core that I'm focusing on is the relational database engine that most of you probably use daily. But Every other bits of the product that come along with it, such as SQL Server integration services, analytics services, or reporting services, all have their unique and individual performance fingerprints. Every server's purposes and resource consumption patterns are completely different, and as we discuss the way these servers' components and features use the resources underneath, I'll discuss how to identify how these pieces of the puzzle fit together, and how you can tailor and tune each piece to best fit its workload characteristics. For those of you that have been a database professional for quite some time, you might remember a time when virtualization didn't exist. For those servers, and servers today that are not yet virtual, the traditional server model was relatively straightforward. You have a physical server that contains our computer resources such as CPU, memory, and interconnects. They have an operating system, such as Windows Server, installed on local storage in these servers, or they boot from LUNs on a shared SAN. You have some form of shared enterprise storage or locally attached high-performance disks connected to the server, and then SQL Server is installed and running in this platform. Most of the time for normal SQL servers, this platform is not running at 100% busy all the time. In fact, most of the time, this activity level is rather low. Most of the time, it sits at a very low CPU percentage utilized, and the bulk of the compute resources in the physical server go underutilized. We were forced to do this because as the server matures and the business utilization increases, we might need more compute resources somewhere down the line. So the right thing to do was when the server was purchased, we overbought hardware in case we would need it in the future before the machine was eventually retired. In actuality, we usually overbought hardware and the workload demands never grew to fill the server that we bought. I equate this to buying a high-performance sports car and leaving it in your driveway idling, and every once in a while taking it to go get groceries, but never taking it to a track or really using the full potential of the vehicle. Because we can't see into the future and know exactly what we need towards the end of the life of the server, this was really the only safe way to provision equipment and make sure that we had enough spare capacity to accommodate whatever the business would throw away. Adding hardware, especially CPU, at a later date was usually not cost-effective. Now, introduce virtualization into this architecture. It's the same physical equipment, just probably with more CPUs and memory. We have the same underlying storage architecture and the same interconnects to get there. What has been added is a hypervisor onto this physical server. This hypervisor allows for multiple compartmentalized operating systems and whatever is installed in them to coexist and run on the same physical server. Each operates in their own bubble and are not aware that the others are there. Allowing multiple operating systems, or OSEs, to run on the same physical machine with isolation between them allows us to make better use of the compute resources in the physical server. Each virtual machine can be assigned its own level of compute resources that it can use up to what the host has available. Modern compute hardware is so quick that usually we can add more assigned resources to VM than actually exist on the hosts. And since these VMs don't usually run at 100% all the time, we can make even greater use of the compute hardware. This hypervisor is essentially a very small operating system. Its resource consumption overhead is tiny. It provides the conduit for running your virtual machines on this physical server and provides all the features available that we need in our data center. Operating systems, such as Microsoft Windows, are designed to have a one-to-one relationship with the physical server they run on. They were never designed to run concurrently with other servers on the same physical platform. The operating systems don't know that they are virtual machines. That's part of why we get such flexibility with these systems. We can literally run just about anything concurrently on the same hardware as long as it's managed properly. I've even got a Windows 3.1 VM somewhere for fun. To make sure that we're all on the same page, let's get some acronyms out of the way. First is our host. The host is the physical server that our virtual machines are running on and the hypervisor that runs on it. The host kernel comprises of all the interoperability components that take the VM commands and get them to the physical compute resources present in the host. The virtual machine is sometimes called a guest. The guest is our virtual machine running an operating system with everything installed inside that operating system and is all self-contained. Think more of the operating system side inside that virtual machine. I look at the VM itself as an object running on the hypervisor that contains the guest operating system and the applications running inside it. This gives me a bit of distinction from operating system level tuning compared to virtual machine level tuning. The VM is how we can compartmentalize the OS so that more than one can operate on the same physical host without the knowledge that the others are there. A virtual appliance is essentially a pre-packaged virtual machine, usually from a third-party vendor, that is easy to deploy and self-managed. You can make your own, but most organizations that I see don't roll their own. The acronym OSE stands for Operating System Environment. In our case, OSE means either Windows Server or Linux installed as the base operating system inside of each of our virtual machines. One of the best features of modern hypervisors is that they provide an abstraction layer between our OSE and the physical server that it runs on. I no longer need hardware-specific drivers running inside my operating system in order to be able to use my physical devices like network adapters and storage. It means that I can back up this virtual machine running on one type of physical server and restore it to a physical server with a completely different hardware topology, and it will power on successfully. The performance or compute capacity of the underlying hardware might change and may alter my VM's performance characteristics, but at least it'll turn on. If you've ever tried to back up and restore a physical server's operating system from one physical machine to another, it almost never works unless you make sure that the destination server's hardware is identical to the source server. Usually there are small differences, such as microcode firmware versions, secondary devices like storage and networking adapters, or even slight differences in disk configuration that can make your restore fail. Because of this, server admins for decades have had to maintain very strict regimens of validating hardware at the disaster recovery facility to make sure that you could actually restore your backups if there were ever the need. Virtual machines do not have that problem. You no longer have to have that dependency of the physical machine's configuration. This abstraction allows you much more flexibility for both the compute platform that you're running on and your disaster recovery component of your business continuity strategy. As long as you're running the same or newer version of the hypervisor and do not have a requirement for certain connected hardware such as persistent memory, which may not exist at the destination host, you can power on that VM on just about anything. Your virtual machines have 4 basic needs. I call them the 4 main food groups, as these must be present for your servers to be able to run successfully. The first is the CPU processor. This is essentially the brains of the operation. This component is what executes our code and delivers our results. The second is memory. Memory is necessary so that we don't have to run everything from a very slow storage medium and can buffer our commands in volatile memory for performance gains. Next is storage. Storage is what holds all of our important data and is essential to contain the data and be fault tolerant so that our data is not lost if minor hardware failure occurs. The storage layer might be physically present inside our physical server, or it might be separated and be shared storage with other servers. Last is our networking and interconnects. This is the mechanism that these servers can communicate to other devices in our data center and could be either network communications or storage communications or both. These 4 make up our compute resources. These are present in every data center globally, but not every set of compute resources are created equal. As we dive through the modules, you'll see the differences in each of these and how we can select and engineer the components that will make our SQL servers both the fastest and the most highly available servers possible. The hypervisor sits between the physical server and the guest operating system. When a command is sent to a compute resources from an operating system inside a virtual machine, it cannot go directly to the physical machine compute resource. Every one of these requests must go through the hypervisor layer's resource scheduling queues and wait in line until the command is processed by the hypervisor and sent to the physical compute resource for execution. Every single thing that occurs inside a virtual machine must traverse these scheduling queues before it can be executed, no matter how mundane or trivial. This is the secret sauce for allowing multiple virtual machines to access the same compute resources transparently. These queues are certainly not visible from inside the virtual machine. After all, they don't know that they're virtual machines, and they don't know about scheduling queues. These VMs think they have direct access to the computer resources that they see. Fortunately or unfortunately, these queues are not always first in, first out. Other tasks can be deemed more important and they can cut in line. Other commands can be deprioritized and sent to the back of the line. These resource scheduling queues are where most people get into trouble with running large workloads in virtual environments. Our goals are to make sure that the amount of time spent in the scheduling queues for each of these requests is kept to an absolute minimum. If we can do this successfully, then the time spent in the queues are incredibly low and the overhead virtually non-existent. This makes our hypervisor scheduling overhead almost zero and barely measurable, which means that we've got bare metal performance, but with all the benefits of the hypervisor. If these queues start to stack up for a lot of different reasons, our workloads start to take a significant performance penalty, and that's where virtualization has historically gotten a bad reputation. I don't know if you've had the opportunity to tinker with containers or not, but SQL Server has been natively supported in a Docker container since SQL Server 2017. Containers are amazing and still continue to evolve at the time of this recording. What is a container, you might ask? Think of it as a virtual machine with your SQL Server and databases in it, but without dragging along an operating system every single time. It has a much smaller operational footprint than a traditional virtual machine. It still has a virtual machine, or maybe physical, but I doubt it, running underneath it, but you just don't have to worry about it. All of the dependencies for your applications that run inside the containers, such as application libraries and executables, are contained inside that container itself. With the introduction of running SQL Server on Linux with the 2017 release made running SQL Server in a container possible. One or more containers can run on an available OSE, which can be a virtual machine and run more than one on a single physical machine. At this point, I'm sure you've also heard of the public cloud. These include platforms such as Microsoft Azure, Amazon AWS, and Google Cloud. Cloud is nothing more than someone else's data center located somewhere around the planet with virtualization on all of the servers and some absolutely amazing automation that allows you as a user to provision and manage your own servers in their data centers. In a lot of cases, this automation will allow you to use these services that have been presented, but they can manage the components underneath and hide them from your view. An example of this is Azure SQL Managed Instance. It's a full SQL Server environment running in a highly available configuration that you can use for your workloads. You do not get access to the underlying operating system, but trust me, it's still there. Their automation maintains and manages this layer and all its nuances for you, so you don't have to worry about it. You just connect to the instance and use it just like you would any other SQL Server instance. This level of automation is amazing, and as time goes on, we'll start to see this level of automation in your on-premises data centers as part of a push for hybrid cloud architectures. However, to get the most out of any of these technologies, cloud or on-prem, we still have to understand the virtualization layer and how our SQL servers interact with the infrastructure underneath to make sure that we provision these components the right way to get the most performance and availability for our databases. To get the most out of our shared SQL Server virtual machines, the single biggest change to realize is that this is a shared everything environment. In the old days, when I had my database servers, I had dedicated CPUs and memory and storage just for my databases. I wanted all the CPU and all the RAM, but did I really need all of that? In most cases, no. The virtual environment allows for all of the host compute resources to be shared amongst all of the virtual machines running on that host. The shared everything environment takes a little bit of getting used to and has to be managed appropriately. The shared everything nature means that high resource consumption by one server could actually impact other virtual machines and make it run slower. If this is managed properly, it isn't a problem, but managed incorrectly could probably be the nagging issue for your servers for at least a decade. You can see on the chart here how we can break out the CPU consumption for our other servers. The orange band at the bottom is a SQL Server DB01. The pink line above it is another SQL Server DB02. All of the other bands of color in there are lesser active virtual machines running different application servers for this particular data center. You can see that our SQL servers are the highest CPU consumers on the host. This is a real screenshot taken from one of the environments that we manage showing how the individual virtual machines can run together on the same physical host. The servers were quite happy to coexist with each other and everything was just humming right along. Now let's get to some specifics on VMware. VMware is a company, not a hypervisor. Technically speaking, VMware ESXi is our hypervisor. Technically, it's also a Type 1 hypervisor, meaning that it is installed by itself as a little operating system on the physical server and doesn't serve any other purpose. A Type 2 hypervisor is something like Windows servers with a Hyper-V role enabled or VMware Workstation installed on your laptop. It's a hypervisor running on top of another established operating system. It can do other things as well as run that hypervisor. ESXi is the little operating system installed on each of the hosts in your server farm. VMware vCenter is a separate appliance that is acting as the coordinator and orchestrator for all of your hosts in your data center. This is a utility that you will probably be interacting with. It provides a single management interface for all of your hosts and virtual machines in your server farm. If you ever hear the term vSphere, it is a suite of virtualization products from VMware, including the vCenter, ESXi, and a lot of add-on tools and packages for expanded functionality. Examples of these add-ons that you might have heard of include tools like vRealize Operations Manager, vSAN for distributed storage, and NSX for virtual networking. One interesting thing to note is that VMware recently started working with the various cloud providers to allow for the vSphere platform to run natively on public cloud provider bare metal hardware. They call this the VMware Hybrid Cloud. Cloud providers such as Amazon and Azure all allow for native VMware functionality on their hardware today. It's a rather tightly controlled architecture with ESXi on the bare metal servers, vSAN for hyper-converged storage, we'll talk a bit more about that soon, and NSX for virtual machine networking. VMware was the first hypervisor on commodity equipment, but it's certainly not the only one. Guess what? Mainframes in the 1960s had their own flavor of virtualization. It was just on proprietary equipment. But for the modern x86 server equipment, VMware first shipped Workstation in 1999 and then the first server products called GSX and ESX in 2001. Microsoft started developing and releasing the Hyper-V hypervisor in 2008 and has been continuously updating it ever since. Linux-based KVM is a Linux kernel extension that allows for paravirtualization on the Linux platform. Companies like Red Hat, Citrix, and Oracle have built management layers on top of KVM to provide enterprise-ready virtualization platforms. Other companies like Nutanix have taken it a step further and use KVM to build their own hyper-converged storage and virtualization package. Other platforms such as Azure Stack HCI have been recently introduced that provide on-premises virtualization platforms but integrate with the public cloud's automation advancements to provide this level of automation in your own data center. At this point, the virtualization platforms are all very mature. I don't have any hesitancy in recommending any of these platforms. VMware arguably has the most tuning opportunities, so I'm starting here. I might sound like a broken record and repeat some very obvious statements here, but virtualization has a significant number of benefits in today's modern data centers. If you have a physical server for every workload in your environment, the odds that you're running all of these at 100% busy are very slim. Most of the time, these machines are very lightly utilized. If we can add more workloads to a smaller set of physical servers but maintain performance, then we don't have to buy as much physical compute hardware. The cost savings that comes along with less physical machine hardware to buy is not just from the computer itself. Every data center has power and cooling that you have to worry about, networking switch ports that cost money, and even the rack space itself can cost your organization if it uses a managed colocation provider. All of this is above and beyond the SQL Server licensing implications of reducing your overall core count, which is usually how your licensing is based. Also, there's the resiliency that is included with the virtual machine layer. Since we're no longer directly pinned to running these VMs on a particular physical server, high availability comes along with these platforms. If a physical machine fails, the virtual machines are restarted onto another physical server that is still running. It usually results in an outage window of no more than 3 minutes if a physical server were to fail. In some cases, that level of high availability is good enough for our workload. In other cases where we may have more strict SLAs, it may not, but it will definitely help improve the platform resiliency. Also, because we don't have to worry about having the exact same physical servers underneath our SQL servers, we can now leverage different equipment on our DR platform. It means we may be able to use the last generation equipment in DR or leverage something like a public cloud provider, which might be cheaper in the long run. No technology, or pretty much anything else in life, is perfect. Virtualization does have some drawbacks. It is an added layer underneath your operating system before you get to the physical compute resources. It is certainly not a trivial platform to manage. There are a high number of default values and management practices that have to be reviewed and maintained before you can get really close to bare metal performance. If these platforms are not managed properly, you can incur a higher rate of outages than their physical equivalent. Another issue may not be immediately apparent. Because these are completely different layers that are usually maintained by different groups of people, in the event that there are performance or availability challenges, you might see a higher rate of finger pointing and blame on where the problem lies. Most of the time, and very unfortunately, the various teams work in near complete isolation. They don't understand the implications of one change of their platform and how it impacts the other layers. Not having visibility into the various layers also means that you may not have the transparency to know what changed in the event that something goes wrong. Because it is an added layer, it could also take more time to troubleshoot performance challenges during an emergency. It could also mean another group of people have to be coordinated and managed for tasks like server migrations. With all the proper amount of planning, transparency between the groups, and people management, all of these drawbacks can be worked through so that they're not significant drawbacks. If these are significant drawbacks in your organization, do whatever you need to do to work with the other organizational silos. Buy them a beer, ask good questions, educate them on what you are seeing in your perspective, and form a good working relationship with these folks. It will be time well spent and will help overcome the major non-technical concerns about enterprise virtualization. In addition to the drawbacks, there are some common challenges that do take some time to work through with these virtual platforms. I stress over and over again that each team needs basic visibility into the other platforms and their perspectives on performance. Without it, the blame between different organizational silos gets in the way of people being able to actually troubleshoot and resolve performance and availability challenges. If these platforms are not managed properly, you can have silent performance killers come out of nowhere. You walk into work Monday morning and everything is working great, and then at 10 a.m., something changes and things are running a quarter as fast. Why? Because these are shared everything environments. The performance characteristics of your servers can change as fast as somebody else can kick off a bad query or an end-of-month report. The components that make up the infrastructure stack underneath your enterprise SQL servers are functionally the same, no matter if they're on-premises or in the cloud. At the bottom of the enterprise infrastructure stack is storage. It could be hard drives inside your server, or it could be a shared SAN. Next up is your physical servers themselves that contain our compute resources. There are interconnects, either fiber channel or networking, that communicate your servers to the storage and allow our physical servers to communicate. The next is your virtual machine enabler, the hypervisor, that is installed on the physical machine server. Skip this if you're still dealing with some physical servers. The next layer is a virtual machine layer. This contains the compute resource assignments that the virtual machines possess, as well as key settings to help maintain performance and manage these layers. The next is our operating system. It could be Windows or Linux, and is where our SQL servers reside. Containers could be enabled on this operating system, or we could install SQL Server like we always have. The next layers are the SQL Server instance. We can have one or more instances installed and running on either the operating system or inside the container on the OS. Next are the individual databases themselves. These databases are the components that store and process our data requests. Higher up above this are the applications that consume this data. It could be web applications or other pieces of the puzzle, or it could be end users with their own set of tools to run analytics, reports, or integrate with this data for other purposes. If you're running your servers in the cloud, all of these layers are still present there. The automated capabilities of the cloud might mean that some of these layers are not visible or accessible to you as an end user of the data. You just use the automation to put some of these pieces together to provision the components that you need. For example, if you're provisioning a SQL Server virtual machine in the cloud, then you pick the scale of the compute resource allocation, then you attach the storage to the virtual machine. Where the storage lives, you don't know. All you know is that you told it to connect a 1 terabyte disk for you to put your database on, and it does it. The SQL Server layer then uses the compute resources that have been allocated and accessible to it to process your data request and retrieve any information that it needs either from physical memory or fixed storage. From our perspective, it's the top tip of a vast array of technical components underneath. Because you're running SQL Server on VMware, we have some specific goals so that you can help monitor and maintain the performance of your critical servers. Our primary goal is to minimize the time spent in the hypervisor's resource scheduling queues. Any time saved from being spent in those queues means we get closer to bare metal performance. We also want to improve our availability, so we can start leveraging high availability features built into the virtual platform to either complement, or in some cases replace, our SQL Server high availability architecture. Our primary goal is to improve the operational efficiency of managing and maintaining these servers. Maintaining the speed and availability of the service is critical, but streamlining our operations to make sure these things stay running is also really important. It means that we can save our time to be more proactive in our environment instead of spending our time reactively fighting fires. I'd much rather be index tuning than dealing with something like a bad stick of memory causing database corruption. As we go through the remaining modules in this class, you'll begin to fully understand all of the details and their nuances of all of these layers underneath your database. If we understand what is possible and how to monitor each of them, then we know how each of these layers relate. We'll then understand how a system responds when a system change is made to any of these components. We'll then also be able to step back, put all of these pieces together to form a much larger picture and be able to holistically see the entire system as an enabler of performance and availability for our databases. Therefore, the next steps are to go through the intricacies of each layer in our enterprise system stack from the bottom up, and then talk through very specific performance and availability techniques. We'll then talk about the management of these platforms and how to work with the various other IT silos, as well as dealing with the not so glamorous topics such as licensing. Great job learning about all the pieces of the infrastructure stack and our approach for the technical deep dive on all of the layers. Next up is Module 2, where we start working our way up through the infrastructure stack and talk about enterprise storage.